Welcome everyone to Design and Analysis of Algorithms. In this lecture, we'll learn about a foundational problem in computational geometry and a classical example of divide and conquer paradigm, closest pair problem. So let's start. First, let us start with this fun story, the dance floor story. Imagine a grand ballroom with n guests scattered randomly on the dance floor. The light dims and the music begins, and the host announces the first dance will be awarded to the pair of guests standing closest together. That is the closest pair problem. Problem is, among this n choose two possible pair of guests, which two are sitting nearest to each other? Formally, we are given n points p1 to pn, and we are talking about two-dimensional Euclidean space, where each point pi has x-coordinate xi and y-coordinate yi, and we define the distance between 2 points pi and pj to be the Euclidean distance, which is dpi pj equal to square root of xi minus xj square plus yi minus yj square. Our goal is to find a pair of points that minimizes the distance dpi pj. Now, this problem has many real-life applications, including astronomy, where there are a set of stars and astronomers are looking at new galaxy and they're trying to find which two stars are closest. They're kind of forming the tightest binary system. Or think of air traffic control. There are multiple flights, but which two are closest at this point, and then we should avoid collision for those flights. And there is many applications in computer vision, speech processing, etc. In fact, there is another problem called nearest neighbor problem, which is closely related, that given a point, what is the nearest point to this point? Think of Shazam when we listen to music. If we play a song, what is the nearest song? And by that, they find a song that we're looking for. Or fingerprint matching. Given a fingerprint, what is the nearest fingerprint? It's a very similar problem. Now, in this problem, for simplicity, we're assuming that no two points share the same x-coordinate or y-coordinate. So all the xi, xj are different, distinct, and all the yi and yj's are also distinct. So let's take one example. In this example, we have 4 points, 1, 8, 2, 5, 4, 7, and 6, 3. These 4 are the points. And this table shows their pairwise distance. And if you compute each of them, you will find this one is the cheapest one between 2, 5, and 4, 7. And distance is basically square root of 4 minus 2 square plus 7 minus 5 square, which is square root of 8. Now we have to solve it for general n number of points. How do we solve it? First, for simplicity, we can start with the easiest case. Let's say one-dimensional case. How to solve it? Pause the video, think a bit, and come back. Okay, I guess you have figured out already. This is just sorting. You can sort them in n log n time, and then you can walk through the list and then find that which two neighbor points have the minimum distance, and that is the closest pair in one dimension. Does it work in two dimension? Again, pause and think a bit. You realize it's not. The same points that we have, if we look at those 4 points and take their projection on x-axis and y-axis, then I will see these 4 points are the projection on x, these 4 points are the projection on y, and these 2 points are closest on x-axis. So these 2 points are closest on x-axis. These 2 points are closest along y-axis here. But then the true closest pair is actually, which we have seen already, these 2 points. So that is neither closest in x-coordinate nor y-coordinate, but when you take both the dimensions together, it becomes the closest one. So what is the simplest algorithm you can come up with? Again, you pause, you'll probably find it's order n squared time. For each point you find there are n minus 1 points, what is the distance, and track the minimum, and overall the global minimum will be the closest pair is order n squared time. And for a long time, people believe it might be tight, but then came divide and conquer, and this simple n log n time algorithm. So to use divide and conquer, what we do is, given a problem, we divide into 2 parts and conquer them separately, and then we combine the solutions. So if we can divide into 2 equal sized halves, let's say t n by 2, there are 2 problems, so 2 t n by 2, and then we can combine it quite efficiently, cn in linear time, then that will imply n log n time algorithm. So in general, it is quite easy to divide the problems in geometry into two halves and then recursively solve them, because the base case is also simple here. But then how do you combine? That could be critical. So let's take one example. So think of this Mahabharata army situation. In one side you have Kauravas, in the other side you have Pandavas. Now, Lord Krishna was neutral. In fact, his Narayani Sena fought for Kaurava. So for tie breaking without loss of generality, let's say we put him also in this. Then if we, this is two sides by divide, then we conquer both sides and we find the closest pair. Maybe in Kaurava side that will be Duryodhana and Karna, they are the closest pair. In Pandava side maybe it's Nakul and Sahadeva. But when we look at globally, then Krishna and Arjun, who are right now in two different regions, they might be the closest. So this combination part can be tricky. And what can happen is all these points, the division that we do, if they're close enough, then we have to check all n square possible distances. With n by 2 here, n by 2 here, all can be possibly the closest pair in general. So it could be or n square. So can we do better? Is there a way to use structural property of the problem so that we don't need to check so many distances, but on linear number of distances, and then we'll be fine. So for that, we'll set up the recursion and continue in the next part.